As channel lengths getting shorter, the influence of lateral electric field is getting bigger than the vertical electric field. So it makes us hard to control the device's off state. To solve this problem called short channel effect, we reduce the oxide thickness. It makes vertical electric field more influential because as we reduce the oxide thickness, the oxide capacitance getting bigger, and it makes the gate channel well coupled. But nowadays, the thickness of this oxide is less than 2 nanometer, so it caused tunneling issue. So now we cannot reduce the thickness anymore. Then how can we increase the capacitance? Capacitance is inversely proportional to the oxide thickness, and in the same time, it is proportional to the permittivity. So to increase the permittivity, now we use high K dielectric, and also to reduce the unnecessary parasitic capacitance like depletion capacitance, and to solve the boron penetration, boron penetration, we started to use the metal gate. First, to find appropriate high K dielectric which substitute the silicon dioxide, we need many requirements. Its K value must be better than that of silicon dioxide, and band gap must be about silicon dioxide's. Of course, it doesn't matter if its gap is bigger than that of silicon dioxide, and also the energy barrier height. Energy barrier height must be apart from the silicon conduction band, and thermodynamic stability, interface quality, and process compatibility, and so on. Anyway, there are a lot of requirements. By the way, there is a way to slightly overcome the energy barrier height and interface quality. To use silicon dioxide as buffer. Between the high K dielectric and silicon substrate, insert the silicon dioxide about 5 Armstrong. Then we can overcome the trap site between these different materials, and also we can overcome the energy barrier height. But as we used silicon dioxide here between these two materials, so we must make some loss. So it's not a perfect solution. There are two kinds of metal gate, which are the solutions of polydepletion and Fermi level pinning. First is dual metal gate. It has advantages that we can use two different metals in the same time. Each metal fits with the different type of MOSFETs, N or P. However, it's not easy to integrate, and there are some problems with the doping, body doping. We call it random dopant fluctuation, which means that we cannot use sufficient dopants for using these dual metal gate. So we do not use it these days. On the other hand, single metal gate is tuning the metal work function. So with this solution, we can tune the threshold voltage untouched by the random dopant fluctuation problem. In this point, the reason we tune the threshold voltage is to design different devices with different purpose, because the device performance is determined inversely proportional to the threshold voltage. So if the threshold voltage is low, then the device performance getting higher, and oppositely, if the threshold voltage of the device is high, then the performance of the device getting low.